Welcome to today's paper reading. Today's paper is titled, Aggregation of Reasoning, a Hierarchical Framework for Enhancing Answer Selection in Large Language Models. This paper was published on the AR14 preprint by Zhangyue and colleagues from Fudan University, National University of Singapore, Shanghai AI Laboratory, and Medea AI Research Center. Recent advancements in chain-of-thought prompting have significantly improved the reasoning capabilities of large language models, LLMs. Current research methods involve sampling multiple reasoning chains and combining them based on the frequency of the answers. However, this approach struggles when correct answers are in the minority. To tackle this issue, the authors introduced the Hour framework, which aggregates reasoning hierarchically and selects answers based on the evaluation of reasoning chains. Additionally, Hour dynamically adjusts the number of reasoning chains according to task complexity. Experimental results demonstrate that Hour outperforms existing ensemble methods and shows superior adaptability and performance across various LLMs. The introduction of this paper highlights significant advancements in natural language processing, NLP, tasks, as evidenced by studies from OpenAI, Chowdhury et al., and Tuvran et al. However, despite these advancements, there remains a significant gap between the performance of these models and human-level expertise in reasoning tasks, as noted by Kabi et al., Valmikam et al., and Ray et al. To address this gap, the paper introduces the chain of thought (COT) prompting technique, proposed by Wei et al. COT prompting encourages large language models, LLMs, to generate a series of intermediate steps leading to the final answer, thereby simplifying the problem-solving process and offering a new perspective on addressing complex reasoning tasks. Figure 1 illustrates an example from the Aqua dataset, where 5 reasoning chains are generated using temperature sampling. Despite the LLM generating the correct answer, B, majority voting incorrectly selects answer, C, due to the prevalence of incorrect answers. Figure 2 illustrates the proportion of samples where correct answers appear in LLM's generations among those where majority voting results in an incorrect outcome across various reasoning tasks. Over 80% of the samples that LLM has the potential to answer correctly, but majority voting fails. Notably, in Aqua and Penguin's datasets, this proportion exceeds 95%. These findings indicate that ensembling reasoning chains, which relies on the frequency of answers, still has significant room for improvement. Table 1 provides a detailed comparison of our proposed Hour framework with other existing reasoning chains ensemble methods. Key features highlighted include Hour's task-agnostic nature, its training-free operation, its plug-and-play capability, and its support for dynamic sampling. These features ensure that Hour is both functional and cost-effective, making it a superior choice for enhancing the reasoning performance of LLMs. In the related work, Chain of Thought (COT) prompting has been highlighted as a significant technique for enhancing the reasoning capabilities of large language models, LLMs. This method allows LLMs to produce multi-step solutions without requiring additional training, which has attracted considerable attention. Additionally, the ensemble of multiple reasoning chains has been explored to improve the consistency and accuracy of answers. Methods such as self-consistency and verifier-scored chains have been proposed to achieve this. Furthermore, the evaluation capability of LLMs has been a focus, with studies showing that LLMs can produce evaluation results comparable to human experts. This capability offers advantages such as customizability and being training-free, which is integrated into the aggregation of reasoning chains in this research. In this section, we introduce the foundational concepts that underpin our approach. First, we discuss standard prompting, where the large language model, LLM, takes a question Q and a prompt T as inputs, generating each token of the answer sequentially to maximize likelihood. Next, we explore COT prompting, which enhances the prompt by integrating the problem-solving process, guiding the LLM to generate a rationale R before producing the answer A, forming a reasoning chain R, A. Finally, we detail the self-consistency method, which employs COT to sample multiple reasoning chains, followed by a local scoring phase where chains with identical answers are compared, and a global evaluation phase where the highest scoring chain is determined. Figure 3 illustrates the workflow of the aggregation of reasoning, our method. It begins with the sampling of 10 reasoning chains. During the local scoring phase, reasoning chains that yield identical answers are compared, resulting in the selection of high-quality chains R1, R2, R3, and R8 for further global evaluation. In the global evaluation phase, chain R2 achieves the highest score. However, the score difference between R2 and R3 does not exceed the predefined threshold theta, indicating a close competition between the two chains. The methodology presented in this paper employs an aggregating reasoning, our approach, which primarily unfolds in two stages: local scoring and global evaluation. In the local scoring phase, the authors utilize chain of thought, COT, to sample n reasoning chains, represented as R1, A1, R2, A2, Rn, n. These chains are categorized into n distinct buckets based on unique answers. Within each bucket, the reasoning chains are scored, and the top k chains are selected as representatives. In the global evaluation phase, a representative from each bucket is selected for assessment. After k rounds of evaluations, the bucket with the highest average score determines the final output. Additionally, the paper introduces a dynamic sampling process that adjusts the sampling of reasoning chains based on the LLM's confidence in the optimal reasoning chain. This process identifies two key answers, A-alpha and A-beta, and terminates the sampling if the margin between their average scores exceeds a predefined threshold theta. Figure 4 illustrates the dynamic sampling process in reasoning chains, where solid circles represent reasoning chains and hollow circles their respective scores. Initially, due to the minimal score difference between R2 and R3, 3 additional chains R10, R11, and R12 are sampled, yielding answers A, B, and E. R10 and R11 are then compared against chains with matching answers. R10 fails to outscore R1, while R11 surpasses R8, advancing to global evaluation. R12, introducing a new answer, E, exceeds the threshold epsilon and progresses. In the global evaluation, R11 outperforms others, and with its score difference with R12 exceeding theta, thus answer B is selected as the final decision. In this experiment, the authors evaluated the performance of our across 3 types of reasoning tasks: mathematical, common sense, and symbolic reasoning. For mathematical reasoning, 6 datasets were used: GSM-8K, Multiarith, Single EQ, SVAMP, ADSUB, and Aqua. Common sense reasoning covered datasets like Strategy QA, CSQA, BoolQ, and ArcC. Symbolic reasoning included tasks from BigBench such as date understanding, penguins in a table, colored objects, and object counting. The authors compared our with several strong baselines, including chain of thought prompting, self-consistency, progressive hint prompting, and diverse. The main results show that our significantly outperforms these baselines, achieving an average performance boost of 2.37% compared to the COT method and 3.09% compared to the SC method. Notably, our demonstrated significant improvements in symbolic reasoning tasks, highlighting its effectiveness across diverse reasoning challenges. Table 2 presents a detailed comparison of the performance accuracy of our against several strong baselines across 6 mathematical reasoning datasets. The table highlights the highest accuracy scores achieved by our, which are underlined for emphasis. Notable results within the same prompt are further highlighted in bold. All methods utilized a GPT 3.5 Turbo 0301 backbone to ensure a fair comparison. The results for Complex Co-T and Complex Co-T-PHP are sourced from Zeng et al., 2023. Additionally, the average performance across all datasets is provided to give an overall perspective on the effectiveness of our and mathematical reasoning tasks. Figure 5 compares the performance of our against various strong baselines in common sense and symbolic reasoning tasks. In common sense reasoning, our shows an average improvement of 8.45% over the SC method and 8.27% over the CC method. Notably, our significantly enhances the LLM's performance on Strategy QA, a task emphasizing implicit reasoning strategies. In symbolic reasoning, our achieves improvements of 5.8% on the date understanding dataset and 8.9% on the penguins dataset compared to the SC method. Figure 6 illustrates the relationship between sample volume and dynamic sampling iterations in the Aqua and GSM-8K datasets. The x-axis represents the sample count, and the y-axis indicates the rounds of sampling. Color variations on the graph denote the range of answers identified during the global evaluation phase across different data samples, with 20 raw indicating the initial distribution of answer counts. Figure 7 illustrates the performance of the answer-oriented reasoning framework when employing various large language models, LLMs, as both the backbone and evaluators in solving Aqua problems. The figure provides a comparative analysis of how different LLMs impact the performance metrics of the framework, highlighting the effectiveness of each model configuration in handling complex reasoning tasks. Figure 9 analyzes the cost and performance of and SC on the Aqua dataset using GPT 3.5. The x-axis represents the cost, the y-axis indicates accuracy, and the size of each point corresponds to the number of reasoning chains. CoTOR 2040 surpasses CoTSC 40 with a 7.2% boost in performance and a 20% reduction in overhead. It also outperforms CoTSC 100, indicating our evaluation of reasoning chains is more efficient for answer selection. The SC method shows saturation beyond 60 reasoning chains, while our continues to enhance performance at 40 and 60 chains, suggesting a superior performance ceiling. The framework introduced in this study significantly enhances ensemble methods for reasoning chains. It employs a two-phase evaluation approach to assess reasoning chains from multiple perspectives, ensuring both validity and comprehensiveness. This framework allows for the dynamic adjustment of the number of reasoning chains based on task complexity, thereby minimizing computational overhead. Experimental results show that significantly improves the reasoning abilities of large language models, outperforming several established baselines. Additionally, adaptability extends across various LLM architectures, with potential for further enhancements. Ethically, the methodology does not involve the collection of personally identifiable information and has been designed to prevent any form of discrimination. The licenses for all datasets used in the research have been thoroughly reviewed. Thank you for watching.